Welcome to this first training module on using the GPUs on Setonix. So for this training, the focus is to understand the availability of the second phase of Setonix and the GPUs that it has, as well as the migration path for our current GPU users on the Topaz system. We're going to cover off the available compute resources as part of phase 2 of Setonix, the migration pathway for Topaz workflows, as well as the available GPU programs that we'll have in the software stack. You can also find out more about the accounting model for the GPU partitions, as also how to schedule and run GPU jobs. So to provide an overview of the migration, we are currently configuring the Setonix GPU system to make the GPUs available for production jobs soon. And the full GPU allocations will be spread evenly across quarters 2, 3, and 4 for the rest of the year. And Topaz will continue to run in parallel until later in the year. So existing Topaz projects can continue to use their Topaz allocations on Topaz. However, would encourage researchers to consider moving to the Setonix GPU partition sooner rather than later, and try to only use Topaz for software that is not yet able to run on Setonix. We also have the call for next year approaching later in the year, and would encourage all researchers to consider carrying out GPU benchmarking of their workflows to include in their applications for time on Setonix next year. It's worth bearing in mind that Topaz will be decommissioned later in the year, along with the associated file systems. So in terms of the migration pathway for our researchers that are currently using Topaz, would recommend these steps to follow. You want to have a look at logging into Setonix if you haven't already, and then migrate your data from the existing Topaz file systems to the new Setonix file systems. You want to have a look at the software and versions that are available on Setonix, and then install any domain-specific or updated versions of software that you may need. You can then prepare your Slurm batch scripts and start submitting your workflows to the scheduler. So some best practices that would recommend is to only move data that is needed on Setonix across. If there's other data that you have, consider whether that you don't need, then consider deleting it, or perhaps moving data that you no longer need to be actively using onto institutional data servers or to your laptop. We strongly recommend not transferring software due to the difference in the underlying hardware architecture. You will want to either reinstall your software, or even consider moving to newer versions or alternative software packages. We also recommend setting up your environments inside the Slurm batch scripts and try to avoid using login scripts, as this makes your workflows more portable when you're sharing them with other researchers or requesting help through the help desk system. And we have some more information regarding the transition of data and some of these steps that we provided for our main Setonix migration from Magnus, and so you may want to consider having a look at that material as well. So for migrating a GPU workflow from Topaz, if you've been through this process from the first phase from Magnus and Zeus to Setonix, it's very similar. Some of the key changes that you'll see in this migration is that the GPU nodes now have 64 CPU cores and 256 gigabytes of memory per node, and there's 4 of the AMD MI250X GPUs as available as cards that will show up as 8 logical GPUs or GCDs available per node, which we'll be talking about in a lot more detail shortly. Some key changes to your job script will be that the account has a dash GPU attached to it for using the GPU partitions. There are GPU partitions to be specifying in your job scripts, and there's also the need to specify how many GPUs per task or per node that you'll be looking at. And again, we'll cover this in more detail shortly. So next we'll be looking at the GPUs that are available on Setonix in more detail. So to provide an overview of what's been made available as part of Phase 2, one of the big new things is the GPU compute nodes. So there's 192 of them. As I mentioned, there's 4 MI250X GPU cards, and each card has 2 logical GPU devices. So there's 8 of those per node, providing a total of 512 gigabytes of GPU memory per node. There's one 64-core AMD Trento CPU with 256 gigabytes of CPU memory. And there's also, of those 192 GPU nodes, that includes 38 nodes which have 512 gigabytes of CPU memory, if you do have higher CPU memory requirements in your jobs. There's 4 200 gigabit connections to the interconnect per node. And so these are very compute dense and highly networked nodes supporting GPU workflows. As well as these new GPU nodes, there's also a significant increase to the number of CPU nodes that were available in Phase 1. So there's an additional 10,088 CPU compute nodes. So there's a lot more CPU time available as well, which will hopefully help with CPU workloads getting through the queue. We have additional login data mover visualization nodes to help support work running on the system. And if you've been using the CPU compute nodes, is a slightly faster interconnect that's been upgraded to 200 gigabits per second. So looking at an individual Phase 2 GPU node, we can see here in the center, there's the Trento CPU, and this is split into these 4 NUMA regions. So this stands for non-uniform memory access. So each NUMA region has its own RAM controller attached to it with 64 gigabytes of RAM for that total of 256 gigs per node. And within those NUMA regions, there's 2 chiplets, and each chiplet is sharing a layer 3 cache. And you can see there's 8 cores there per chiplet. So in that first chiplet 0 on the left, you can see that there's those cores labeled C00 through to C07. And we've also got labeling for the thread placement as well. So because these threads have simultaneous multi-threading, you can have multiple threads per core. And so we have some numbering for that as well. Below, you can see that each of these NUMA regions are attached to the MI250X cards that contain these 2 logical GPUs each. You can see in this diagram, we're providing some of the bus numbers and the GPU numbers associated with them, and we'll talk a little bit more about that shortly. And then each of those cards is connected to one of the network interface cards that are at the bottom there, which is the connection out to the Slingshot interconnect. So we then can start zooming in on the Phase 2 GPU architecture. So each Setonix GPU node has 4 MI250 cards with these logical GPUs or graphics compute dies that I've been mentioning, and the diagram on the right there is one GCD. So you can see each GCD has 110 compute units with 64 streaming processors per compute unit and 4 matrix cores per compute unit, as well as 64 gigabytes of memory. And for more information on the GPU architecture, we recommend having a look at AMD's CDNA2 white paper that goes into a lot of detail. So for comparison, the Topaz GPU queue nodes had 2 of the NVIDIA V100 GPUs. So for the CDNA2 compute unit, the shader cores, which are denoted here in C, are used by the standard HIP APIs and kernels. There's also matrix core units, which have these matrix cores that are similar to the NVIDIA tensor cores. And these provide accelerated small matrix multiplications in half, single, and double precision. And you can access these using specialized APIs or libraries, such as RockWMA. the wavefronts on the AMD GPU architecture, which is similar to the NVIDIA Warps, 64 lanes wide rather than 32. So you may find this might be something that you want to change in your GPU programming if you are developing your own software. And again, for more information, we recommend having a look at that CDNA2 white paper. So to bring us on to the GPU software available on Setonix, there's a number of applications that have active development for the AMD GPUs, and we're actively adding modules for GPU-enabled builds of some of those popular software. And so watch this space as we continue to make those available. And also it's worth checking with your software vendor or looking through the documentation to see whether your software supports the AMD GPUs. So in the software stack that we have on Setonix, the GPU-enabled modules will have the AMD-GFX90A suffix. So the GFX90A is referring to the GPU architecture. And there will be several bare metal builds available with the full GPU functionality of the software. We also have our container technologies. So we've been using Singularity to run GPU accelerated containers. And so some of these are available as modules, but there are some limitations. Currently, they only scale up to one node, and a subset of the containers can only use one GPU, which is worth being aware of. But the AMD Infinity Hub has a collection of containerized applications that you can have a look and see if your application is covered by those containerized applications. And there's also the E4S initiative, which provides a number of containers as well. So for the GPU accounting on Setonix, the GPU allocations are separate to the CPU allocations in Slurm. And so because of this, when you are running GPU jobs in your Slurm batch script, you'll need to use your project ID with the -GPU suffix. This will only be for the Slurm GPU requests. When you're asking for time in your job script. In terms of your files on the file system, they'll all still be in your standard project allocation. It's also worth noting that the GPU nodes consume 512 SU per hour, which is 4 times the amount that the CPU nodes consume, and this corresponds to the difference based on the energy consumption. Finally, to look at the GPU allocation usage, you can use the Pawsey account balance tool in a similar manner to your existing CPU allocations. So for shared access on the GPU nodes, there's 8 cores and 32 gigabytes of memory associated with each logical GPU or GCD. And so you can see there, we've highlighted those in those red boxes. And Slurm will account for the large proportion of the node resources you request in a similar way to our CPU nodes. So if you're asking for half of the memory, and less of the cores or GPUs, then you'll be accounted for half of the node, and similarly for the cores or the GPUs. So whichever the greater proportion is, that's the amount that will be charged through Slurm. And we strongly recommend requesting 8 cores per GPU, even if you aren't planning to run on them, because this will result in more optimal scheduling for everyone making use of the shared access. So here we have the examples for the Setonix GPU accounting. And in this table here, we're looking at the greatest proportions and how much is charged. So for the first 2 examples, we have the nodes being requested in exclusive mode. So here the job's using all of the GPUs, cores, and memory and being charged 512 SU per hour. In the second example, it's running on only 1 core and only using a little bit of CPU memory, but still using all 8 GPUs. But regardless of whatever resources we used here, because it's in exclusive mode, it still gets charged 512 SU. For the first 2 shared examples, we're looking at one example, which is just requesting 1 GPU with the associated 8 cores and 32 gigs of memory, corresponding to 64 SU, or 1/8 of the 512 SU. The second example here for shared is asking for half of the node resources in each case. So that corresponds to 256 SU. And then these remaining three examples, some of the things that are being requested are higher proportionally than others. So 2 GPUs is the highest proportion here, corresponding to a quarter of the SU. We have the memory here being half of the memory, corresponding to half of the SU. And here, 32 cores is half of 64. And so that corresponds to 256 SU. So that brings us to scheduling jobs on Setonix. So if you're looking in Slurm, you'll notice that there are 3 new GPU petitions available. The primary one that you'll use for production jobs is the GPU petition, which contains 134 GPU nodes. As we mentioned, we have 64 CPU cores and those 8 logical GPUs or GCDs per node, with 256 gigs of CPU memory per node, or 32 per logical GPU, with a wall time of up to 24 hours. In addition to that, we also have the GPU dev petition, which is 20 nodes that we've put aside for debugging or developing GPU software. These have the same node configuration as the GPU petition, apart from a 4-hour maximum wall time. And these nodes are not for production work, to ensure that they're available for interactive sessions doing debugging and development. So please don't use them for production work. And over time, depending on the utilization of these nodes, they may be repurposed back to the GPU petition. So we just have enough nodes to ensure that there's some there for researchers that are looking to do active GPU development. We also have the GPU high-mem petition, which contains those 38 nodes that have higher CPU memory of 512 gigabytes per node. So in terms of requesting exclusive access through Slurm, as I mentioned, it's really important to include the -GPU suffix on the project account, as well as specify the GPU petition that you'd like to use, which could be the GPU dev, or GPU high memory, depending on the type of work that you're doing, as we just discussed. The number of GPUs per task, or the GPUs per node, is the recommended way of requesting GPUs through the Slurm batch scripts. If you look through the Slurm documentation, there are a couple of other ways of requesting GPUs, but we strongly recommend using these two because they're currently working on the system. And for an exclusive job, there's that -- exclusive SBatch directive that will request exclusive access, so you're the only person running on the nodes you've requested. When you're running your srun, we strongly recommend specifying all of your command line arguments in terms of the number of nodes, processes, and in particular the number of cores that we've specified here, as well as the GPU bind closest to encourage the GPU, the Slurm, to place cores near the GPU when it's running. And we'll be talking about that in a lot more detail shortly. For the shared node access, again, the GPU suffix on the project name, the GPU petition you're looking to use. It's a best practice to request your CPUs in multiples of 8, corresponding to the number of GPUs that you're requesting, just to ensure that you're receiving the right amount. So for the CPU to GPU binding for optimal performance, it's worth noting that the ordering of the cores, as we see here, doesn't quite correspond to the ordering of the GPUs. And so you can see the zeroth, the initial numbering of the cores actually corresponds to the 4th GPU, and then the 0th GPU is corresponding to sort of the 6th numbering of the underlying cores. And so for good performance, it's really critical that you're aware of which processes are associated with which GPU when you're running on the system. So there's a number of different controls that you have for working with this. And the first one is checking the GPU availability. Those Slurm directives will restrict the available GPUs to processes that are running on the system. And you can check how this is working with the ROCm-SMI program, particularly with the --show HW option. So if this is an example from a job that is sort of running on one node exclusively, so all of the GPUs are showing up for this process, and you can see that we have the GPU IDs on the left there and the corresponding bus IDs on the right. And then in this next example, this was taken from where I ran two shared jobs on the same node, each requesting 4 GPUs. And you can see in one job, it received 4 GPUs and the corresponding bus IDs, those ones on the right on the diagram, and the other job received, again, 4 GPUs and the corresponding bus IDs from the left side of the diagram. So this allows you to start to get a feel for which GPUs are being requested for the configuration that you're asking in Slurm. This is a further example from exclusive access where I was requesting GPUs per task equals 1, and you can see each process got its own GPU with a different bus ID, which is what you'd like to see. You can also restrict GPU visibility with wrapper scripts, and so there's an environment variable called rock visible devices that restricts the GPUs that are visible to the HIP runtime. And so this wrapper script can be used in your Slurm batch scripts to select which GPUs particular processes can see. And so this snippet shows where we're coming up with a name for the wrapper script, and this is just select GPU underscore and the Slurm job ID. So there's a different wrapper script for each Slurm job. And then we're catting the script, which is just here between this line and the EOF line, to the name of that job that we've set in that first line. And the wrapper script, all it's doing is exporting that environment variable and setting it to the local process ID. So each process will get its own GPU effectively, and then it's running the first argument to the wrapper. And so this is a really helpful way of getting a number of different processes, each with their own GPU device. And you can combine this with your CPU binding, which allows you to control the ordering of the placement of your processes onto the CPU. We have a script called generate CPU bind, which is available to generate bindings if you'd like to do that. So the command is just there, and you then provide these bindings through srun. If you'd prefer not to use the script, it's also possible just to specify these bindings yourself as just a comma separated list of numerical IDs of the CPU. So that's possibly a lot to take in. So we have a very detailed step-by-step guide in our documentation that I'd encourage you to sort of read through and give it a go. And feel free to come along to our upcoming migration Ask Me Anything sessions, or submit a help desk ticket if you're getting started with this and looking to navigate it, because it is quite detailed. So there, I guess the controls that you have to control your placement of your processes, threads, and GPU work. A really good idea is to also confirm that the placement you think you're requesting is actually happening. And for this, we recommend using a Hello JobStep program that we have courtesy of Oak Ridge National Labs. And you can sort of clone and install this program and put it in place of your normal job to see what is actually happening when your job runs. And so here you can see the ID of your sort of MPI process in OpenMP threads, what position, and so this corresponds to those hardware thread indices that we saw in the diagram earlier. Which node, if you have a multi-node job, it can be helpful to know which node particular processes are running on, as well as the HIP runtime GPU IDs, the actual node GPU IDs, and the GPU bus IDs. So for this example, we have 3 processes running on different hardware threads or different cores of the CPU, and with access to these corresponding GPU bus IDs. So for more information, I'd encourage you to have a look at our Setonix GPU Partition Quick Start Guide that has a lot of this information in more detail. And also it's a good launching pad, as it will have links into our documentation from there to follow up with more information. We also have our Setonix Migration Guide, which is focused on researchers that are currently using Topaz in terms of making the transition across to using the Setonix system, as well as our general Setonix user guide and our supercomputing documentation. In terms of our migration training material and recordings, definitely have a look for the follow-up session, which will look into installing and developing GPU software with Setonix. As a recording, we also have our live training events of this training material, and our Ask Me Anything sessions where you can come along and ask questions. And if all else fails and you do hit an issue and you need help, please contact us via the help desk so we can follow up. On that, I suggest checking out the second GPU migration video shortly.